Okay, so we're going to do is geoprocessing. Sorry, it took me a long time. So, the geoprocessing, it's under the spatial infrastructure. If we put in here file geodatabase, we could do geocoding, digitizing, and geoprocessing. So, the objective is learning about spatial analysis functions, including overlay, clipping, and buffering, using map overlay to analyze multiple spatial criteria, understanding differences between spatial joints and overlays, geoprocessing with manuals, ArcGIS toolbox, and model builder. So it's like vector data analysis. So we will talk talking in detail about the map overlay, union, intersect tools, and then we will move on to talk about proximity analysis like buffering and some manipulation techniques like clip, erase, append, dissolve. We will have a lot of example on the way. So we already did the exercises, so now I'm just summarizing some of the tools and give some of the background information. So map overlay, it joins features based on common location and forces features to split when they overlap each other, and creating new features enforces one-to-one cardinality between between features in order to join attributes. So that here map overlay. So map overlay combines two layers to create a new output feature class containing information for both of the inputs and the polygon from a geology layer and from a land ownership layer have been combined to produce a new set of polygons. Such new polygon has been given the attributes of the origins, and each contains information about both geology and ownership for the same feature. So the output layer might be useful for selecting areas containing certain geometry-bearing rock formation on public land and would be suitable for mineral hunting. So because this material is from Mary Beth, the book, and she's the professor in geology, so they talk about mineral hunting. And overall function fall into two categories, so those that do not combine attributes and those that do. So functions that do not combine attributes, also called extract functions, include clip and erase. In extraction, the input feature retain their attributes, but the attributes of the clip or erase boundaries layers are ignored. So the two functions that combine attributes include intersect and union. So union preserve all of the features from both inputs. Intersect only keeps feature common in both to both inputs. We will learn that in detail, and we will show the pictures so that it's a lot easier to understand. So map overlay combines geometry and attributes of two feature maps to create new output. And input and overlay maps must be spatially co-registered. So they can only work with two data layers at a time. So overlay, why overlay it? So we found that spatial joints are not always a good solution to a problem, and features do not always fall neatly inside others. And overlay provides a way to split features so that there is always a one-to-one correspondence. So let's look at the problem with spatial joints. The task is we gather statistics on the total length of roads in each land use category. We want to associate the land use type with the road and inside spatial join problem. But the road, we can see here that the road does not stop at the land use boundary. A summarized join won't work with a category called data. So the three different land use categories apply to the single road segment. So map overlay splits features that splitting a road to assign attribute to each piece that we can cut the road into pieces. So that a map overlay forces the road features to split at the land use boundary. Each new segment falls inside one land use category. So the tables can be now joined, providing a basis for calculating total road length in each land use category. So the intersect and the union functions are related to spatial joins in that they correlate features based on their spatial relationships to each other. However, spatial joins fall when spatial features do not overlay exactly. Consider the map of roads and land use here. I already mentioned here, and we can look that the roads already being cut within the polygons. So the roads are the line segments. So the state government has requested a report of the total miles of road falling into each land use category. At first glance, a spatial join might be considered to generate this information, and by joining the land use polygons to the roads, they might expect to get a field showing the land use each road crosses. So, however, the single selected road highlighted here crosses three different land use. Join option no land use class would be assigned for the road because it does not lie entirely inside a polygon. A summarized join would do no good because a nominal data type such as land use class cannot be averaged. The ideal solution would split the road into three sections and assign the land use to each section, and this is what overlay function do. So thereby enforcing a one-to-one relationship between features and enabling a perfect correspondence when joining the tables. And the original single road is now three sections, and each segment is the output table is assigned the attributes of the land use polygon containing it. So types of overlay we will look at now. There are three. So as a point in polygon point, each point in polygon and line in polygon and polygon in polygon overlay. So we will talk about one by one, and we will not talk about like boundary issues for now. But if it's like a little point, we will say either it's in this green polygon or this orange polygon. For the line, yeah, we separate the line. There was start point and end point, so we cut it using the boundary. And the same here. Some part is belong to the purple color, the other is green color. For a dot, we do not split them either in this polygon or the other polygon, or you could say a point that could, if it's fuzzy boundary, we could say it could be both in both boundaries in both polygons, but that's not that accurate either in polygon yellow or in polygon green. So we choose one for a point. Okay, point in polygon overlay. So use assign polygon attributes to point. So we assign each house point the associated school district with education statistic, allow buyers to compare schools. So like I mentioned, your house, it could be at the boundary, but usually they wouldn't split a house into different parts. Okay, overlay on point and polygon. So like here, so we have an input and output, and then we can see the point table tree. We have elm tree, maple tree, and elm tree. And for the input for polygon table, we have rural, urban. So we could say that the elm tree is in rural, maple tree in rural, and the elm is in the urban area. Okay, so next we will talk about the points and polygons. So points and polygon attach land use polygon attribute to each school. For points and polygon overlay does the same thing as the spatial join. Overlay on line and polygon, that we can see that the line table and race arch in urban and rural and urban area. So we have a race arc, and that we will see which landscape they belong to. So line and polygon overlay, we use assign polygon attributes to lines. So associate geologic units with each section of string. Use rock type to model infiltration. That's in our project that I don't think we will have time to go over those examples. But here the lines and polygons, each streams acquire the geologic unit from the polygon it lies inside. Streams are split at geologic unit boundaries. So the polygon on polygon overlay. So one combines spatial features by producing all possible polygons. So we have a geology and slope classes we combine. Steps to overlay is we put them together. So combines features spatially producing all possible new features. And combine attribute tables bringing original values from each table and assigning to each new feature. A new spatial data set is created with these features and attribute table. So we have to look into detail. So for example, the green part, we have the feature is that the name is Cenozoic, and this part we have the slope, and we combine. So we will copy original values from both tables from each new polygon. So when we have a new polygon that we kind of like add, we use the same field and we add we have more columns, so we can see shape ID, everything, infiltration, everything is from here. So and then we expand it. It's just like adding columns. So for this overlay, it's just think about we add more columns to our table for our features. So we're going to talk about the two types of overlay that's very important, is union and intersect. So map overlay with attributes occur in two forms. So union combines two polygon layers and keep all layers and merging the attribute for both layers, and intersect also merge the attributes but retains only the areas common to both layers and may be performed with points, lines, or polygons. So at first it might be difficult to understand. We will break down later and summarize it later. You will see this again. So for overlay, we keep the common areas. So intersect, we keep common areas. But for union, we keep everything. So keep all areas polygon to polygon overlay only. So this is an example for union. So a union creates a possible polygon from the combination of features in two polygon layers. Here shows a union performed on geology and slope class layers to create a landslide hazard map. Landslide risk depends primarily on two factors. The strength of the geological units, sandstones are less susceptible to sliding and than shales, and the slope, and the lighter areas in the slope class map have lower slopes, and the dark areas have higher slopes. A union produces a new feature class with new polygons, each of which processes the original attributes of its parents. The new feature class can then be evaluated for the various combination of slope and geology that may constitute a landslide hazard. And the intersect operation with two polygon layers is similar to a union, except that it only keeps the polygon layers areas that are shared by both input layers. So this function provides a way to find out where two or more condition hold simultaneously. So the founded of a class of problems known as suitability analysis, evaluating a landscape to find which areas best serve a given purpose based on a set of functions. For example, one could find the potential habitat for a species with specific fundamental environmental requirements. Imagine that during a routine evacuation for a parking lot, the city engineers discovered pockets of enhanced radioactive material in the Approach formation. They are recommending that homes on the Opich formation have a basement random test to rule out possible unhealthy levels of random. We can use an overlay analysis to determine which areas of homes need to be tested. The slide shows here a series of maps in overlay analysis. So the first map shows a portion of the residential area, and second shows the epoch formation outcrop area. So these two layers are combined in the overlay, which result in a third layer composed of the areas occurring in both input maps. So the output layer contains residential areas that lie on the epoch formation. So here we have the hazard mapping, residential areas, epoch formation, so area of both. So habitat analysis with intersect. So these image are a real species of snail inhabits the Black Hills. So this snail prefers limey soils in cool and dense coniferous forest and is rarely found above an elevation of 1,600 meters or below 1,200 meters. Each dataset elevation geology vegetation is queried to find the areas meeting the specific condition, and the result 3 layers are intersected to find where all 3 conditions hold. And the habitat polygons in the output contains the full attributes of all 3 layers. Should that information be needed, such a map would help biologists create sampling strategies for counting populations, analyze whether the habitats are interconnected or widely separated, and make decisions about forest management to protect the snails. And the snail's habitat demonstrates polygon on polygon intersection. Intersection can assign attributes from polygons to lines or points within them. The roads and land use problem described in here is an example of line-in-line polygon intersection, assigning land use categories to the roads. This slide, 2 images on top, is an example of line in polygon intersection and assigning land use categories to the roads. And in A, so here we see that in polygon intersection is used to assign a geologic unit to each stream reach and useful for estimating stream loss to groundwater. One can also intersect points with polygons or point in polygon intersection. A realtor might have a point feature class of houses for sale and intersected with polygons representing school districts in order to be able to list the school for each house. So in B, we can see and note that a point in polygon intersection is equivalent to a simple inside join with the point layer as the destination, even though they use different tools to do it. So whereas the union function requires 2 polygon input layers, the intersect command is more versatile. Both input and overlay layers may contain points, lines, polygons, and the output geometry may vary, but it cannot exceed the dimensionality of the lowest input. So map overlays, here we will talk about the first one is intersection in detail. with examples. So we can see the image here. The Boolean operator with the keywords is and. So cat and dog problem, you need to have them both. So input may be points, lines, or polygons. Preserve features within area common to both within input and overlay Boolean operation with keywords and. So analysis with the intersection. So preserve features with area common in both input and overlay. So we can find this tool in ArcGIS Toolbox. So this is ArcMap. Now, ArcGIS Pro, the interface is a little different. And resultant layer. So only building polygons that intersect flat zones with combined data fields. So that we can see. So the analysis with intersection. So that you can see with the intersection, we combine the attributes and everything together. So we intersect land uses in 1 kilometer buffer around power transmission line. So new thing has attribute from both inputs. So query, display, analyze new shapes. So in our exercises, we did select by attribute and select by location. So that kind of it will have the feature that asks you to do intersecting. So that's intersecting is very important to understand the spatial concept here. So where areas the union function requires two polygon input layers, the intersect command is more versatile. And both input and overlay layers may contain points, lines, or polygons, and the output geometry. So the output geometry is may vary, but it cannot exceed the dimensionality of the lowest input. If the input are both polygons, the output may be points, lines, or polygons. So in top, so we can see the two circles might represent the drug-free zones around two schools. So the polygon output shows the area of overlap. The line output could become a boundary on a map. So if the inputs are both line feature classes, so the output may be lines or points. These lines might represent hiking trails, in which case the line output will find locations where two trails travel together. So the point output could find trail intersections that need to have signposts placed on them. So if the inputs are polygons and lines, the output may be points or lines. If the circle represents the area around the school where sex offenders are forbidden to live, the line outputs could provide a list of the streets and addresses, a range that are off limits. If the city intends to put a sign every street entering the zone, the points output would estimate the number of signs needed and where they should be go. So that's how it shows here, intersecting polygons and lines, choosing lines or points. So here, intersecting points with anything else with yield points. So intersecting in the ArcGIS Pro, that we can see from here that the interface is a little different. But here, intersect, we compute a geometry intersection of the feature. So the feature or portion of feature which overlap in all layers and all features classes will be written to the output features. Input can have a different geometry types, so like I mentioned, line, polygon, and everything. So here we intersect. Let's see, here we have Manhattan streets. That Manhattan street intersect. So we can see that here we intersect shape area, shape length, and we see the intersect and see intersect results that streets will have all the fire company information here. So we kind of combine and add them there. And we could do summarize street length for the fire companies, and you just do summarize statistics. The second one is like Boolean operation like a keyword or cat or dog, no matter what you have, as long as you have a pet, just like how you say. But for the first one, you have to have. If you say you are a pet lover, that you have a cat and dog, you must have a cat or a dog at least. But here, as long as you have a pet, it's fine. So overlay is union. It's like you add more rows together. So input and overlay must be polygon layers, and preserves all maps features from input and output layers by combining spatial extents. So which means that their tables have to be everything is the same. We just add more rows to our maps. So here it preserves all maps features from input and output layers by combining spatial extents. Or you can add more things. So for example, here I have it here is overlay 2 polygon layers. So the example we did neighborhoods and zoning and land use, resulting outputting layer has combined attribute data of the 2 inputs. So we contain all the polygon from the inputs whether or not they overlap. So here attribute table is like we adding them all together. So it doesn't matter you have one you have a more column, the other you do not. The only thing is that if the sum column you do not have, it will be just become into a null value. So here it's just like we add more rows together. So union result is polygon with the data that will combine. An overlay operations summary here, that attribute not join, it will be clip and erase. So we put input and overlay and output, we can see that. But for the attribute join, so clip and erase, your attribute is not changing, but the attribute for the intersect and union changes, either adding more columns or rows, I would just say like that. Combining overlay functions. So here summarizes the different overlay operations that can be performed using 2 polygon input layers, including the extraction function, clip, and erase, which do not combine attributes, and the intersect and union functions, which do. And clip and erase can also accept point and line feature classes for one input, but the boundary input must contain polygons. And the output feature classes will have the same geometry as the input classes. So unions and polygon on polygon intersections are similar. So a word about when to use each may be helpful. The primary use of intersect is to find areas where certain conditions overlap, and the primary use of intersect is the primary use of intersect is to find areas where certain conditions overlap, and typically the input layer occupy different regions, as do the elevation range, limestone, and conifer layers shown here. So the goal is to find the area common to the inputs. Although the attributes from each input are combined in the final table, the attributes themselves are sometimes of little interest. So in the snail habitat problem, the pertinent attributes were already pre-selected using queries, and the main goal was developing a map of the overlaps. So here, in a union, the primary goal is to combine the tables. And generally, the input layers are fully occupying the same region as the geology and slope class layers do in here. And it is expected that the entire map area will remain, but there are the new features will contain the attributes of both features. So that we will have is we will contain the attribute of both inputs. After a union, the usual next step is to perform attribute queries to find areas with specific combinations of attributes, or to symbolize the combinations to show areas of interest. In the landslide hazard example, we might have extracted the shale in high slope areas and down and intersect to show where the high hazard areas exist. So the hazard is either there or not there. With a union, though, we are able to analyze different combinations of geology and slope to access potential impacts on slope stability. So the length and area changes, like clip can change the length or areas of feature on the boundary, and we can see that geodatabase feature class have a shape and length, shape and area fields that are automatically updated for us. So another length or area based on fields are not updated. Slivers. So overlaying layers often produces small extraneous polygons or lines called slivers. Sometimes these slivers represent real features, however, more often they arise when overlaying layers share some boundaries, such as voting districts and counties. In theory, the boundaries should match exactly, but in practice, new data sets have been corrected to this level of integrity, and these slivers do not represent real combinations of values and are a nuance when calculating statistics of performing subsequent operations. This is often desirable to proven slivers when overlaying. And silvers. So tolerance can be used to reduce problems with silvers, and tricky to set. No good if they are too small, will degrade accuracy if too large, and affects output layer only, not the input layer. And the XY tolerance. So an XY tolerance can be set during an overlay operation, and this tolerance specifies the minimum distance between vertices, and it will combine vertices that fall close together, setting an appropriate tolerance during an overlay while eliminating many slivers. However, the tolerance applies to all vertices, and using a tolerance may degrade the accuracy of the dataset. Caution should be used in setting tolerances that are large enough to correct silvers without shifting other vertices an acceptable amount. It may also be remembered that outputs from an overlay that uses a tolerance generally have a lower geometric accuracy than the original layers. And slivers are especially troublesome when multiple layer overlay or analysis operations are planned, because the errors propagate and multiply with each successive step. If XY tolerances are being used, the generalization of the boundaries becomes progressively more severe and may significantly affect the geometric accuracy of the results. It is impossible to avoid this impact, so users should be aware of what is happening and have realistic expectations for the spatial included in metadata for the final output. So the effects of tolerance that we can see union perform on district and counties using different tolerance settings. So map manipulation we're going to talk about is dissolve, and here you will get from ArcGIS Desktop is that apply only to polygon coverages. So removes boundaries between polygons with the same attribute value, like you can see the green lines, like you have a 3 district, it belongs to the green line, it's fine. So it's just like Duval County, you have Arlington, you have a lot of districts, it doesn't matter, you belongs to Duval County, okay? Then you can dissolve. And here the same like streets, not polygons, you can do line features. Dissolve lines on street names, choose an attribute to dissolve polygons on habitat classes. So a dissolve is used to group features together based on whether they share the same value of an attribute field. For example, the road segments here have the name street name main street. So we can see here, but they are separated. There are separate features. A dissolve based on the street name field would yield a new field a new file in which dissolve can also be used to remove lines between polygon features that share the same value. For example, the map in here shows podenser pine stands of different ages. Dissolving on the cover type field removes the age boundaries and yield polygons based on the cover type ponderosa only. So the output from a dissolve operation may produce either single features or multi-features. A multi-feature exists when multiple unconnected areas consist a single feature, as when the severe Hawaiian Islands are combined to produce one state feature. The orange polygons constitute may individually feature. After the dissolve, if the multi-feature option was selected, then all of the orange polygons will belong to one feature and turn into a new layer with a different color. If the multi-feature option was declined, when the data set will have many orange features. So when features are dissolved, the output layer is a new file containing the single attribute on which the dissolve was based. However, the user can specify additional fields to summarize the information from the original features. For example, in the dissolve here, one might request the average canopy percentage of each output polygon based on averaging the canopy percentages of the polygon before the dissolve. So the dissolve, so that we use the common field value to remove interior lines. So the common one, like here we have north, east, north, central, or mid Atlantic. So the same field, and we dissolve combine some of the states all together, and you just have a one field, so that you do not have a name anymore. You just have a subregion, and you have subregion, and you will have a total everything. It will sum up everything for you. Sum. All right. So that's the dissolve result, and you kind of like just. For Pacific, you add everything together. Mid-Atlantic, you add everything together. South Atlantic, you add everything together. So dissolve example, here another one, you have states, but you need regions. So subregions, and you dissolve it. So here is the dissolve tool in ArcGIS toolbox, and this is the old version, and the new version is just geoprocessing that I showed already. And statistic field that you can select everything, but everything you just sum up. So aggregated field can be summarized, and in a statistic type. So the result that we already see from the newer version for ArcGIS Pro. So buffering is another commonly used GIS and analysis function. It is used to identify areas that will fall within a certain distance of set features. Buffers can also be created for points, lines, polygons. It could be used to find the 100-yard drag-free zones around schools or sensitive protected areas with 100 meters of a stream. We can buffer negatively to determine setback limits from the edge of a piece of property. Buffers can also create a simple rings or multiple rings. We can even use an attribute to apply different sizes of buffers. For example, buffering primary roads by 200 meters and secondary roads by 100 meters. Buffering is often combined with overlay to solve a problem. For example, a national forest might be considering adopting a ban or harvesting timber with 200 meters of a road, creating buffers around the road and intersecting the buffers with a timber map could help the manager estimate the total amount of timber rendered not harvestable by such a ban. When buffering, we have the option of storing the resulting polygons as graphics in the map layout, or saving them as a shapefile or geodatabase feature class. If we plan to use the buffers for an overlay step, we should use the second option. And finally, we should know that buffering lines and polygons in a time-intensive process. If we are planning to buffer a layer with more than a few hundred features, be prepared for a long wait. Okay. So, a buffer is constructed to delineate areas that fall within a certain distance of a set of features. Buffers can be created for points, lines, or polygons. They could be used to find 300-yard drug-free zones around school or sensitive protected areas with 100 meters of a string. Negative buffers can be applied to determine setback limits from the edge of a piece of a property. And buffers can be created as simple rings or as multiple buffer rings that attribute. An attribute can even supply different sizes of buffers for different features. For example, buffering primary roads by 200 meters or secondary roads by 100 meters. And buffers are created for each individual feature's MA overlay. And this option might be appropriate in analyzing the distributions of soil in buffer around wells. In many cases, however, it is best to dissolve the buffers, which gets rid of the boundaries between them and removes the overlapping areas to create a single region. Here shows the difference in result obtaining when the buffers areas of the buffers are of interest. Then dissolving is non-dissolved buffers. They would be grossly estimated because the overlapping areas will be counted many times. And finally, the buffering is an intensive process, and the time involved creating quickly as the number of features increases. So any steps to reduce the number of buffers created at one time will facilitate analysis, for example, by performing query before buffering rather than afterwards. So our next tool is append. So the append function is used to combine the feature or two or more layers and place them into an existing target feature class. So the appended layer must have the same feature type as the target, both polygon, both lines, or both points. So the two layers must also share the same coordinate system. Overlapping of layers is permitted. And the treatment of attribute table uses in append requires some consideration. If we wish to combine the attribute information from both layers, and attribute fields must have the same definition and must occur in the same order in both tables. So if the tables differ, so one type as the target layer, then the information will be copied in the input layer has the same name and data type as the target layer. Then the information will be copied into the target. Fields without matching names will not be carried into the target. So the append that we have another one. So we add or more data sets into an existing data set. So it's more like you add more you add more rows in your data set. It's just like you combine them, kind of like union a little bit. So and merge. So merge, that merge is similar to append, except it creates a new feature class and offers more flexible treatment of attribute table. Instead of insisting that the two tables match, it allows users to specify fields to include in the output feature class and table they will come. It's just like you add more rows together, kind of like the idea of union. So a merge combines multiple input data set of a same data types into a single new output data set. So efficient overlay. That overlay is time and memory intensive. Minimize number of features. Dissolve vegetation before intersecting with other layers. So geoprocessing. So all these we mentioned is all geoprocessing. So it is the operations on the geographic information, one of the basic functions of a GIS, and it includes operations related to data analysis, management, and conversion. And multiple geoprocessing operations can be linked to create process. So here, the geoprocessing tasks we can do projection, conversion, and spatial analysis and data management. So the geoprocessing is executing analysis functions and tools, stringing together analysis function to achieve a result. So GIS analysis involves many functions that operate on data objects such as feature classes or table. Geoprocessing applies one or more of these functions in sequence to solve a problem or investigating the property of data sets. Most ArcGIS tools operate on any allowed data type in performing a road buffer. For example, one may specify a coverage, a shapefile, or a feature class from a geodatabase, and the tools make the necessary allowances to execute the function on the various data type. A few tools operate only on certain data types and ArcGIS Advanced licenses. So, for example, provides the user with a suite of additional tools that work on coverages. Geoprocessing framework, that tool.log box, this is the old version, and you can do script, Python script we did many times, and command lines and models. So Arc Toolbox, so dockable window in any ArcGIS application. So this is the Arc Toolbox. So right now it's in the Arc catalog. So when ArcGIS we have it there, and it just like everything would just follow, and it was interesting that they called it project pane, and then later they changed it back to our catalog pane. So the map overlay identity, so we should talk about this earlier, but identity is like Boolean, is more keywords as and or. So preserve map features within an extent defined by the input. For example, if you want to define here, like you want something like this. So it preserves map features within area extent defined by the input. So vector data analysis, we already talked about buffering. So buffering, we will not go in detail. So like advanced buffering, we can do multiple ring buffering and more work. And then the clip, so we will move to the map manipulation as changing the map layer, but distinct from map overlay because spatial and attribute information are not combined in output, often part of pre-processing prior to the analysis. So that clip, we already show in the map. It's just like you use the clip feature as a cookie cutter. You cut it. So generate a new map area that includes feature of inputs that fall within an area extent of clip coverage. So that this is clipping. You want something here, and out clip will be like that. So this is the old version for clip. So differences between clip and select by location. So clip is clean cut, and select by location, you can do intersect and dangle some of the edges. So clip, you can see that clip or cut feature based on a study area, so topology and a central business district. So clip problems. The problem straight can cross boundaries, like you can see those dangles, as I mentioned, those dangles. So buildings can cross boundaries, and clipping can be misleading. So there are some issues you have to be aware. And erase, that you remove something, like you cut something. This is like in previously you cut something, you have the remaining here. But for erase, it's the opposite. You get the remainders. So removes from input map those features that fall within an area extent of erase coverage. So for the erase clip, the clip, you get the feature that within like a cookie cutter, but for erase, you cut the part, you have the leftovers. So map manipulation for append, we just talk about it, and we append things together. I have to move the slides together. I didn't do a good job right now. So, and split is the opposite of merge. You divide into map to two or more coverages, like you create zone 1, zone 2, zone 3, and then you put them here. So map overlay resembles a spatial join, but it splits features when they partly overlap, and this function enforces a one-to-one relationship between features when their attributes are joined in the output table. A map overlay comes into two basic types. A union keeps all the features from both layers, and intersect keeps all the features that are common to both input layers. Attributes from both layers are joined together in the output, and a dissolve combines features within a data layer if they share the same attributes. This function can be used to convert many street segments into a single line feature or to remove boundaries between puzzles with the same zoning. And we talk about buffer. So buffer are polygon constructions that are enclose the area within a certain distance of features. Buffers may be created from points, lines, or polygons, and they may be constructed as a single or multiple rings. Append and merge allow feature classes with the same feature type to be combined as a single feature class, such as merging two adjacent quadrangles to make a single file. Map overlay and spatial analysis are generally best done using a project coordinate system, especially if one anticipated determining areas and length as part of the analysis. Geoprocessing involves stringing together a sequence of commands during spatial analysis. Spatial function may be executed from the menu Arc2 box, the command line model builder or scripts. We will talk about model builder next. Okay, and the shape area, shape length, and shape perimeter fields in a GeoDatabase feature classes are stored and updated automatically. Other area based on length based fields such as area, acres, or road kilometers are not automatically updated. So length and areas of features stored in shapefile must be updated manually. So we have to be aware when we're working on GeoDatabase. No, geoprocessing. So thank you very much.